All right. Hi, everyone. My name is Melody. I am joined here by my teammates Nayeon, Ethan, and Julie, and we are presenting the paper DiffusionDet, Diffusion Modeling for Object Detection. It comes out of the University of Hong Kong, partnered with Tencent AI Lab, a prominent AI lab coming out of China that specializes in object detection and computer vision. This paper is the first diffusion techniques, first time and first research done for diffusion on object detection, so it's pretty neat. So here's a little bit about the paper. It's a preprint from November of 2022 with 103 references and 6 citations. Here's the paper if you'd like to access it, as well as the code that was made available last November as well. So a little bit about DiffusionDet first. The authors of this paper initially started with a hypothesis that the noise to box paradigm is analogous to noise to image. So in diffusion modeling that we've seen recently, we've seen this noise to image process in which we're denoising this noisy image here and creating something like this. The same concept is can be applied to bounding boxes. So we have a set of noisy boxes as displayed here. We can denoise and generate this set here of denoised prediction boxes using diffusion modeling techniques that we've recently studied with a diffusion process Q as well as the reverse process of P theta. So a little bit of object detection first. As we all know, object detection targets input target pairs with images X, their corresponding sets of bounding boxes, as well as their classification labels represented by C here. The bounding boxes specifically are defined by their center coordinates represented by an XY pair, as well as their width and height. So here are some examples of object detection. These images that we're going to show have actually been run through the pre-trained models that the authors provide on the GitHub. So here we can see this image of a crowd where we have several people as well as some cell phones. Here's an image of some farm animals. We see a horse, some birds, a cow, as well as an example here of a busy highway with several cars and even a motorcyclist and a person. So we know object detection has many different applications. Previous object detection historically has relied on region proposals with predefined input requirements, but with anchor points and anchor boxes. These predefined inputs require separate algorithms for those region proposals and further box pruning, resulting in complex architectures that are needed on top of the actual box regression method, as well as the classification label defining. So in order to improve this, some methods have come out recently, including faster RCNN, which introduces the region proposal network, or an RPN, that generates object proposals from an image's feature map. These object proposals are then used for the box regression and object classification process and are used in pair with the feature maps. Even improving that further, we have Facebook's detection transformer method, or DETER. DETER uses a CNN backbone, learnable object queries here in this step, as well as introducing bipartite matching in the final step, forcing a one-to-one matching between prediction boxes and their ground truth boxes. One weakness that DETER showed was the need to declare a fixed number n of object queries in the beginning. This querying process can be thought of as learning a better spatial localization of the image in this transformer, given that all objects utilize that self-attention in the transformer. The issue here is that having to set that fixed number of object queries in the beginning may limit the amount of objects you can detect in a scene. So we've seen that previous object detection methods have used region proposal networks, learnable object queries, anchor points, anchor boxes for region proposals. The nice thing about DiffusionDet is that DiffusionDet doesn't require any of these. DiffusionDet's noise to box process utilizes the idea of initializing random boxes, conducting a series of steps to then giving you these final predictions without the need of those learnable queries or predefined input. So here is the general architecture of DiffusionDet. Here you see the input image partnered and paired with its ground truth bounding boxes. The input image is fed into the image encoder to extract the high level features and then fed to the detection decoder. The important thing to note here is that the actual diffusion process is applied directly to the ground truth boxes, not to the image itself. So we have our ground truth boxes here, we apply Gaussian noise, and we're able to get a set of what we call noisy boxes. These noisy boxes are then fed to the detection decoder, and alongside the feature maps from the image encoder, we can predict classes as well as the object boxes. So the main contribution that DiffusionDet has to object detection in general is this idea once for all training. This decouples training and evaluation. So what does this mean? This means that we can train the model once and apply it for many different inference cases, providing for flexibility depending on if you want to prioritize inference time or your model's performance. So the first aspect of this once for all training is the idea of dynamic boxes. The word dynamic itself means progressing and changing. And in this case, we're talking about during evaluation setting the number of boxes. That number can change. So you can train, let's say, with a number 300. So we start with 300 noisy boxes paired with its ground truth boxes, and we can get a prediction. So keeping in mind that we trained with 300 boxes, we can also take that during evaluation and set our number of initialized boxes to 300 as well. With dynamic boxes, we can also inference and evaluate with less than 300. We can evaluate with 50. We might get faster inference times here. But we also can evaluate with more than 300, in this case 301 or 500 or 1,000. In that case, we might have longer inference times, but more precise results. And what's different about this compared to other methods is that at this point, when the number in evaluation exceeds that than in training, other methods like deter actually see performance drops. With DiffusionDet, as you increase the number during evaluation, you see performance increases. So in the end, there's a trade-off again between inference time versus performance, allowing that flexibility that you can choose to prioritize one or the other. The other aspect of once-for-all training is the idea of progressive refinement occurring in the detection decoder. The idea is we can reuse the decoder head and iterate more steps for better performance. The idea here again is a trade-off between inference time and performance. So you can choose to iterate more steps and get more precise boxes. However, that comes at the cost of your inference time. And again, compared to other methods like deter, iterating more steps improves the performance of DiffusionDet's results. And in other cases, like deter, it actually decreases performance, which we'll explain further with some graphs. But for now, we're going to jump into
generated images, self-driving cars, augmented reality, virtual reality. It's all around us.
see the architecture, and Julie will be explaining DiffusionDet's architecture in depth some more.
Okay, thank you, Melody. Can you see my screen?
Yes.
Okay, perfect. I'm going to go over the architecture and training for DiffusionDet. This is the train loss pseudocode. It takes as input the raw input images and then the ground truth annotated boxes. So we have the batch, the height, width, and the 3 RGB channels. Then for the ground truth boxes, we have the batch, an asterisk, and 4. 4 is the center coordinate X, center coordinate Y, height and width. And the asterisk is because the instance number in each image will vary. Here we have a horse and a person, so that's 2 instances, but it could be 3 horses, 3 people. But we're gonna pad that asterisk to a fixed number n. So we can do that n train number to be any fixed number that we want. We're just going to pad the ground truth boxes to n number of noisy boxes. And we're gonna just randomly concatenate noisy boxes until we reach n boxes. Next up, we're gonna take the raw input images and we're gonna feed them to the image encoder. The image encoder can be a CNN ResNet or transformer-based SWIN. And it's just going to get a lower dimensional, higher information feature map from the images because it's computationally intractable to run all the noising steps and the denoising steps on the raw input images. So we're just gonna take that feature map and use that as conditioning input to the detection decoder. Next up, we're gonna apply signal scaling. So the padded boxes, we're gonna apply a scaling factor. The authors found that they need to scale the boxes as well. The scaling factor controls the signal to noise ratio. We can see here with a higher scaling factor, as time goes on, the signal to noise is maintained for longer through the time steps. Before a smaller scaling factor, that signal to noise degrades quite quickly. And for object detection, they really want that signal to noise to be maintained. The authors hypothesize that it's because the box representation is very fragile. It's just center coordinates and then the size coordinates. So just a slight perturbation would change the definition of the box. So they really want a higher scaling factor to maintain that box definition. Next up, we're going to corrupt the ground truth boxes. We're going to apply Gaussian noise. So T would be a random time step T between 0 and T equals T. Epsilon is the normal distribution noise. And then the padded box corrupt would be the square root of the cumulative product of alpha at time step T times the padded boxes plus the square root of 1 minus the cumulative product of alpha at time step T times the noise. We're essentially adding the noise to the padded boxes. Let's break that down. This is the forward noise process. We can see some terms here like N for normal distribution, but let's extract the marginal here. This is the noisy latent at time step T. This is the conditioning input, the padded boxes. This is our equation right here, square root of the cumulative product of alpha, square root of 1 minus the cumulative product of alpha times step T times epsilon, the noise. And the alpha term is just the cumulative product. So the multiplicative product of all the time steps following the variance schedule. The authors choose a cosine noise schedule in this case because they didn't like a linear schedule. In previous works, we used a linear schedule because Jonathan Ho et al. Used it in their paper and they just tried it, but they found that the latents are almost purely noise. So it destroys information too quickly. It drops to 0 too quick. So they just chose a well-known mathematical function, the cosine curve. They liked that it's a little bit more tapered, a little bit more smooth, not very abrupt at the extremes. So at T equals 0 and T equals T, it's pretty maintained. The drop-off is in the middle, and we can see here the information is retained for longer, and it doesn't dissolve to noise until the latter latents. Next up, we're going to send the corrupted padded boxes and the extracted feature map and the time step T to the detection decoder. The detection decoder is going to take these boxes and crop the feature map into a region of interest feature crops, and it's going to use its detection head to continuously perform box regression and classification, refine these noisy boxes into predictions. The detection head shares parameters across all time steps specified by a time embedding. And then it takes the class and the box prediction along with the ground truth to compute the set prediction loss. We can see here the predictions on the left. 2 of them are assigned to ground truth labels, but this green box here doesn't have a corresponding ground truth label. We're going to pad the ground truth labels with no object classes. Now, to account for class imbalance on the no object, we're going to tweak the weights lower. So that way it doesn't, we can focus learning on the actual ground truth labels. There's going to be many different ways to match up the boxes. So what we really want optimally is to minimize the loss of the match between the ground truth and the prediction. We're going to use the Hungarian algorithm to compute the Hungarian loss efficiently. It's a linear combination of the negative log likelihood of the class label along with the box loss, which is a generalized intersection over union, and the L1 displacement. Next up, we're going to go to inferencing. This is the infer pseudocode. It takes as input the images, that we're going to make predictions on, the sampling steps, and the time steps. So in each sampling step, it's just how often we want to run this loop. And then the time steps are the skips in the denoising process that we're going to use. And then we're going to encode the images to extract the feature map. And we're going to begin from the noisy boxes this time. So we learned to add noise. Now we're going to denoise. So we start at the beginning with noisy boxes padded to n noisy n evaluation boxes. So that n evaluation box can be different from the n training boxes. We want a uniform sample step size, so we're going to use the line space to get even intervals. We're going to have t and then -1 for the beginning, and we're going to reverse that because we're going back evenly in time. We make time pairs, so t1, t2, t2 to t3, all the way to 0 and -1. Now for time now and time next in the time pairs, we're going to use the detection decoder to make predictions. It gets the noisy boxes, the extracted features, and the current time, and it's going to make predictions. And then once it makes those predictions, we're going to use the DDIM to get the next noisy boxes at the next time step. So the DDIM is a denoising diffusion implicit model. It's a non-Markovian reverse process. So the Markov chain is just abbreviated. So the inferencing is accelerated. It's very quick. It doesn't visit all the denoising steps. It does produce accelerated inferencing, and it's really great for this object detection task because it's deterministic, meaning that the generation is very stable given the input. We don't want a lot of fluctuation in the output, but for a more creative task, we definitely want that diversity. So we don't want something deterministic. So that's why this accelerated deterministic DDIM works for object detection here. Then we want to do box renewal. So any noisy box that we didn't like, we drop it off. And because all the noisy boxes in the denoising process are just randomly sampled from a Gaussian distribution, we're just gonna pull and introduce new noisy boxes. And hopefully we're gonna pad it to that n evaluation number again. And hopefully some of these new noisy boxes are going to be better estimates than before. And then this would be the inner sampling loop that we run and hope that it gets better with each sampling stage. And then we're going to output that the final box coordinates and the class labels. Next, Nayan.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Just going to go over the training schedule. Thank you.
Okay, thanks, Julie. Can you see my screen?
Yes, yes, we can see, yes.
So now let me explain how the authors experimented with the DiffusionDet, and this is the parameters the authors set for the training. So they used the two data sets, the MS-COCO and LB 0.0, and for the MS-COCO, it is widely used for the other vision models because it contains a lot of images and categories. But compared to this COCO, LBS is more challenging data set because it contains more than 3 times the number of categories in the COCO. And it is long-tailed data set, which means the images and the categories are highly imbalanced. And they used the ResNet 50 and the swing transformer to construct the image encoder. And they used the Zapier initialization for the detection decoder. And for the robust training, they used the data augmentations. So they used the random flip, random crop, and the random resizing. And they trained the model using 8 GPUs, and they used the mini batch size 16. And for the optimizer, they used the AdamW. And after the training, they inferenced the samples with following these 2 steps. As we explained before, DiffusionDet refines the prediction from the Gaussian random boxes. And after that, they selected top 100 bounding boxes from the MS COCO, and they selected 300 boxes from the LBS data set. And then they applied non-maximum suppression for the more accurate predictions. And as Melody explained before about the once for all, there are two properties of the DiffusionDet, and the first one is about the dynamic boxes. So this is the change of the performance according to the number of bounding boxes. And they compare the deter transformer and the DiffusionDet. And there is a one premise that they train these models to generate the 300 bounding boxes. And we can see that both models' performances keep increasing until they generate these 300 boxes. But after that, we can see that deter's performance is start to decrease. And this is because deter and the other object detection models' limitation, because they are dependent on the fixed learnable queries. So to generate more than the number of used for training, they use the two techniques, the concurrandom and the clone. And we can see that concurrandom is better than clone because clone is just generate similar boxes that generated from before. But concurrandom generated new boxes, so it can guarantee the diversity. But we can see that DiffusionDet's performance is keep increasing steadily, even though they exceed the 300 bounding boxes. And the other strength is the progressive refinement. And as we've seen in the before slide, DiffusionDet can improve its performance by increasing the bounding boxes. So we can see that when generating 500 boxes, it shows the best performance above here. And by iterating the sampling steps, its performances keep increasing. But however, the other object detection models, such as sparse RCNN and the deter, they don't have these refinement properties. So they don't use the detection decoder multiple times. So this is how DiffusionDet can improve its performance by iterating the sampling steps. So we can conclude that DiffusionDet, there is no limit to the generating bounding boxes, and they can increase performance by iterating the sampling steps. And this is the benchmarking result on the data sets. The authors compared the other method and the DiffusionDet with using ResNet 50, ResNet 101, and the swim-based transformer. And they compare the DiffusionDet by increasing its refinement steps. And here, this one step means they didn't use the refinement steps at all. But still, we can see that its performance is outperforming than the others. And it's same as the LBS data set. And they found that the performance is best when they use the swim-based transformer. And the other interesting thing is that when we compare the best performance on these two data sets, the growth of the AP score in the LBS is better than the MS COCO. And it means that the refinement properties brings more gain to this data set. So we can conclude that the refinement is more helpful for handling the challenging data set. And to find the best parameter, they did the evaluation study. So the first component is about the signal scaling, and they found that using 2.0 is optimal in this case. And it is actually relatively big numbers when we considering that image generation using 1.0 and panoptic segmentation using 0.1. And this is because by increasing its ratio, they can denoise the noise on input signal, and it can improve its accuracy on the object detection algorithms. And the next one is about the ground truth padding strategies. And the authors show that using cat Gaussian show the best performance when compared to other method. And this is because CAD Gaussian is better able to model the complex distribution of images than the others. And for example, this one CAD uniform, it assumes that the pixel distribution is all the same. So it is too simplistic to capture the non-uniform distribution. And this one CAD full is used in sparse RCNN. And this one is more flexible than the CAD uniform, but still it is too general and difficult to capture the correlation between the pixels. And they proved that using DDIM and the box linear together showed best performance. And because DDIM estimates the bounding boxes for the next steps, and box linear, it removes the undesired predictions. And they set the 0.5 for the box linear threshold. And as we've seen before graphs, DiffusionDet's performance is keep increasing no matter how many generating the bounding boxes, but it tends to better perform when the number of bounding boxes for evaluation and the training are matched like here. And the default setting of here is 300. And this is the correlation between accuracy and the speed. So by increasing the bounding boxes and by increasing the sampling steps, its performance is keep increasing. But we can see that the FPS is slowed down. So this is the limitation of the DiffusionDet. And this is the random test. So random seed is initialize the diffusion process by generating the initial noise. So according to the random seed, the change can be different. So the authors, they tested the 5 models for 10 times per the seed. And all of the AP scores are around 45. So it means that a DiffusionDet can reproduce the result stable, and we can see that DiffusionDet is a reliable model. Okay, so now Ethan will go over to our demos and conclusions.
Ethan, we might not be able to hear you.
Again, can you hear me now?
Yes.
Yeah.
There we go. Fantastic. So to validate some of the claims made in the paper, we ran some demos and experimentations of our own. We used the pre-trained weights provided by the paper, and we ran them on 2 different systems, one consisting of an M1 Max CPU and one consisting of an Intel i5 CPU. So the first thing we wanted to compare was the difference between the pre-trained weights based on the MS COCO dataset and the pre-trained weights based on the LVIS dataset. As you could see, the MS COCO was able to capture considerably more subjects in this example than LVIS was. And when we change subjects to farm animals, even though LVIS is able to capture a significant amount of animals, it does have some inconsistencies. Like with this chicken, we can see 2 bounding boxes, and we could see that this chicken was actually labeled as a duck. For these reasons, we felt that MS COCO was more consistent, and we chose to use these pre-trained weights for the rest of our experimentations. So the next thing we wanted to compare was small-scale detection scenarios versus large-scale detection scenarios. So you could see in a large-scale detection scenario, we were able to detect 12 instances in 1.3 seconds. On the flip side, when we have only one object, we detect it in just over a second, which is very similar to this, even though we have considerably more objects. The reason is because one of the benefits of diffusion detection is that your inference times are based more on your initialized parameters than they are on the subjects or content of your images. So another example here, you could see 9 instances of farm animals detected in just over 3 seconds, and 2 instances also detected in just over 3 seconds. So next we moved on to testing some of the main claims of the paper. This included the dynamic boxes. So first, we took an image and we initialized it with 300 random box proposals, and we were able to find 11 instances of people. As claimed in the paper, by raising the number of proposals, we were able to find more instances of people, which you can see here. Finally, we wanted to test the progressive refinement claims. So we took the same image and we ran it for 1 sample step, 4 sample steps, and 8 sample steps. As you could see, The increase in the amount of sampling steps did indeed increase the ability to bound objects from 14 to 17 to 19, but it dramatically increased our inference times, considerably more than the increase in the amount of objects we were able to bound. So during this presentation, we've covered how object detection can be solved in a generative way by adapting the diffusion noising denoising process into the noise to box process. We've seen how we can replace computationally expensive learnable queries with random boxes. And by iteratively refining these boxes, we can indeed accurately bound subjects. So some of the strengths of this approach include its generalizability, or in other words, its ability to recognize a diverse set of subjects without the need for additional training. So you could see in these images, from people to animals to even balloons, it's able to recognize all of these without any need for additional training. Another one that's been mentioned quite a few times is the dynamic boxes. In large-scale detection scenarios where you don't necessarily know exactly how many objects you need to detect, such as in crowds or on the road, an approach like diffusion detection is very strong as it has an unlimited number of potential bounding boxes. So some of the weaknesses of diffusion detection are that it's slower than YOLO and RCNN, actually considerably slower. Even in the most favorable situations where we have a low number of initial random boxes and only one sampling steps, it's still only able to achieve an FPS of 30. This is compared to CNN-based approaches, which average an FPS of 150. So for small scale scenarios in situations such as this, in small scale scenarios where you have either one or two objects, it's not ideal to use an approach such as diffusion detection. Another issue we found with the paper was a lack of visual examples. Most of the figures that you've seen throughout this presentation were actually created during our experiments and our demos. That was because the paper actually only provided 4 figures for the full noise to box process, which was pretty lacking in our opinion. Finally, we realized that the performance increases are pretty negligible in comparison to your increase in inference times. So we can see here that even as we increase the number of sampling steps, our average precision really only increases by 1. And we've seen in earlier slides how increasing the number of sampling steps drastically increases our inference times.